Hi everyone, I'm Yunhui. Today I'm going to present our work, a hypothesis testing approach to sharing logs with confidence. This is a joint work with Lu and Professor Gunter at University of Illinois at Urbana-Champaign. Logs generated by systems and applications contain a wide variety of information such as timestamps, the size of input and output files, and CPU utilization. This information plays an important role in scientific research and analysis of production systems in industry. For example, for large companies, sharing system logs would guide academic research to be more relevant to their problems. And small companies often outsource their log analysis to third-party services for anomaly detections. Despite the increasing need for log sharing, companies are often unwilling to share their logs due to concerns about information exposure. These exposure include not only direct leakage of user identifiers and system settings, but also indirect evidence of unreleased products, performance metrics, and hardware information. Although direct leakage can be protected by sanitization, anonymization, or encryption, the indirect evidence is much harder to detect and protect. Meanwhile, this evidence may leak important business secrets. For example, the performance metrics can create targets for competitors, and leaking information about hardware used in a company can increase the cost of obtaining this hardware in the future. There are two different types of protections for log data: differential privacy and empirical obfuscation. Differential privacy has been used to prevent side-channel leakage from timing and message size. However, applying differential privacy can be challenging for high-dimensional complex data, and for some applications, we cannot afford the information loss incurred by noise injection. Compared to differential privacy, empirical obfuscation such as sampling, scaling, and aggregation are more applicable to high-dimensional complex data. For example, they have shown to be effective in protecting Google production logs. However, these empirical methods suffer from a lack of quantitative analysis on protection effectiveness, making them hard to generalize to new applications and scenarios. In this work, we introduce an end-to-end framework for log sharing. We design a framework that is generalizable to different systems, offer user-specific protection criteria, quantitative analysis on the risk of exposing sensitive information, and adaptive obfuscation methods. First, let's formalize the problem. Suppose the user Alice wants to release a set of log files, but is concerned that the log may leak some sensitive property, such as the type of hardware Alice is using to generate the log. We call this sensitive property SP and define CP to be the set of possible values for the sensitive property. For example, suppose there are two types of machines Alice might be using: a cluster of 8 core machines represented by S0, or a cluster of single-core machines represented by S1. The goal of Alice is to release the log files without leaking information about whether she used S0 or S1 to generate the logs. While releasing the logs, Alice might also share some information that she thinks to be non-sensitive. For example, the program that is used to generate the logs. The non-sensitive information offers important context about the log files and are useful for researchers and analyzers. On the adversary side, suppose an attacker, Bob, wants to infer what type of machine Alice used by observing the log files shared by Alice. Besides the shared log file, we assume that Bob also knows the non-sensitive properties shared by Alice and a set of possible values for the sensitive property. The goal of Bob is to infer the sensitive property. In our case, he wants to guess whether Alice used the 8-core machines or the single-core machines in her experiments. The process of guessing the sensitive property can be modeled as a distinguishing game between the adversary Bob and the user Alice. The process is as follows. First, Alice randomly picks a sensitive property S and generates the log file ls. Then Bob obtains a guess based on his background knowledge and the log file. If Bob's guess is correct, he succeeds in the attack, otherwise he fails. Therefore, to protect the sensitive property from being leaked in the log file, we want to bound the probability that Bob succeeds in the distinguishing game. Formally, we propose the definition of log indistinguishability. Let Cp be a set of possible values for the sensitive property. The log generated by program P is gamma log indistinguishable on Cp if, for any pair of C1 and C2 in Cp, no adversary can succeed the distinguishing game with probability greater than 1 plus gamma divided by 2. Satisfying gamma log indistinguishability means that sharing the log does not greatly increase the adversary's chance of successfully inferring the sensitive property. So, how do we verify whether log files are gamma log indistinguishable? Actually, formally verifying gamma log indistinguishability can be extremely challenging. On the one hand, it is challenging to identify all the metrics influenced by the sensitive attribute. On the other hand, obtaining a theoretical proof on the influence of a software or hardware setting is generally impractical. However, the challenge in obtaining a theoretical guarantee doesn't mean the end of the world. We can still test whether the log files are gamma indistinguishable and identify potential violations of the property. In fact, similar approaches have been used in other areas, such as software testing and randomness tests. For example, it is challenging to prove that a complicated system is bug-free, but by performing unit tests and integration tests, we can identify bugs and reduce the chance that the system fails in practice. Similar to software testing, we design a testing framework for log indistinguishability. The input is a set of parsed log and the protection specification, such as what properties are sensitive. Then we perform a set of hypothesis tests to check whether different metrics in the parsed log satisfy gamma indistinguishability. We call these tests the indistinguishability tests. If any of the tests is failed, we perform empirical obfuscations to hide the sensitive information and redo the tests. Although passing all the indistinguishability tests does not guarantee that the system satisfies log indistinguishability, it prevents obvious leakage of the sensitive information and increases the user's confidence in sharing the logs, just as performing software tests increase our confidence in the software system. Then, how do we design the indistinguishability tests? Suppose we have two sets of parsed log files, L0 and L1. Both L0 and L1 contain n log files collected by repeatedly running the same program for n times. L0 is collected with the sensitive property equal to S0, and L1 is collected with the sensitive property equal to S1. Then we can test the indistinguishability property with the following hypothesis tests. The null hypothesis is that L0 and L1 come from the same distribution, while the alternative hypothesis is that L0 and L1 come from different distributions. If L0 and L1 are indistinguishable, none of the test statistics should be able to reject the null hypothesis. Therefore, we consider the test as passed if we cannot reject the null hypothesis. Otherwise, the test is failed. Next, we demonstrate the process of performing log indistinguishability tests and obfuscations through a case study on Spark event logs. We collect Spark event logs generated by training a multi-layer perceptron model. The logs contain 15 numerical attributes, such as the running time and the I/O size of each task, and 4 categorical attributes, such as worker ID and task ID. The sensitive information we want to protect is the hardware used to train the models. Specifically, we have two clusters. Cluster 1 consists of 10 servers with 8-core processors, while Cluster 2 consists of single-core processor servers. To perform the tests, we generated one set of logs using each cluster. Each set contains 100 log files generated by repeating the training process 100 times. We perform the test under gamma equals to 0, meaning that we want to test whether the adversary can succeed the distinguishing game with probability greater than random guess. We use two tests as an example here. The length test compares whether two sets of logs have the same length. For Spark event logs, the length of the log file is determined by the number of parallel tasks. Therefore, since 8-core machines can run more parallel tasks than single-core machines, the logs generated by 8-core machines are much longer. Here, the number in the table is the p-value of the hypothesis test. P smaller than 0.01 means that we reject the null hypothesis that the two sets of logs are indistinguishable with high confidence. To prevent the log length from leaking information about the hardware, we performed random sampling and selected a fixed number of tasks for each log file. This way, all the logs have similar length, and the p-value for the length test is greater than 0.01. Hence, the length test is passed. Next, we perform the moving average test on the numerical attributes. We first calculate the moving averages of a numerical attribute within a fixed window size, and then test whether these moving averages come from the same distribution. The figure on the right shows the distribution of the executor runtime of the same task in different repetitions. The blue bars represent the running time on 8-core servers, while the orange bars represent the running time on single-core servers. The two distributions are significantly different because 8-core servers finish the tasks much faster. Therefore, the moving average test fails. To hide information leaked by running time, we first scale the numerical values to have them share the same distribution median. However, scaling alone does not completely hide the sensitive property because the two distributions still have different variance and skewness. We further designed probability integral transformation to align the two different distributions. Basically, we generate a new distribution f-mix by mixing the samples from the two distributions. And for each sample in the original distribution, we find their corresponding values in f-mix and use that to replace the original value. After the transformation, the moving average no longer leaks the sensitive property because their distributions are statistically indistinguishable. The test results indicate that after the obfuscations, the log files are unlikely to leak the sensitive property through its length and moving average of numerical attributes. Finally, we evaluate the utility of the log files after the obfuscations. We designed 16 questions about system performance, such as what is the bottleneck of the system? How many stragglers are there in the system? We evaluate the number of correctly answered questions after the obfuscation and use it to understand how much utility loss is incurred. After the obfuscation, for 69% of log files, we can still answer all the questions correctly. However, for around 30% of the log files, we made mistakes in a few questions because the noise introduced during the obfuscation. In the paper, we also performed other case study on the hardware performance counter dataset. We also designed other tests such as frequency tests, moving average tests, and differential privacy tests. And we proposed other obfuscation methods such as generalization, suppression, noise addition, and aggregation. Please refer to our paper for more details. In summary, in this work, we proposed a generalizable log testing framework. Our framework helps users to identify the risk of leaking sensitive information, quantify the risk using statistical tests, and mitigate the risk with empirical obfuscation. Moving forward, we would like to apply the testing framework to data sharing in other applications. Thank you for attending our presentation. I'm happy to answer any questions.